I've been finishing all my days early. After 7 p.m. Like he just wants to sit down like that.
What's your size?
Yeah, it's all gonna be 0. But do you want to sleep at 10:30 and
This and then
what? Okay, so just and I wake up at 6.
Yeah. If you're not behind one,
Getting my life together. Slowly.
so yeah, airdrop.
Oh yeah, there's gonna be a lot of people. Yeah, it's in the. No, it's because of the Black History Month. They're gonna, yeah, they're having like, I think it's different countries from Africa, and they're having like food like that. I'm going because I have to.
Three times. So epsilon 1. What about the exchange? An epsilon is going to be the same. Well, I think this exchange is going to be 3 times C. And I want you to write it as epsilon equal to main C, and you have this number C, and 0 is the
Yeah.
Bob wanted us the K.
Yeah.
Have you ever derived it in class?
No, but I want you to do it.
I see.
Here.
So we just use look up the formula online and then just calculate.
Just verify that you get the same answer.
Oh, we have to derive the K.
Yeah, you have to derive. Okay?
They like get $4 for stuff. Wait, what?
All right, guys. Let me tell you more or less what the solution is here. Here the solution is going to be that you're going to have. Let me write first the strain. The strain tensor. Because here we're working with number 1 as a direction in which there is actually strain. So let's see, if number one is pointing down, this could be 1, 2, and 3. And I'm assuming that this solid is deforming with stress in this direction, but it cannot expand to the other 2 directions. So it just deforms in this one, but it stays the same in directions 2 and 3. Because of that, you're going to have a non-zero value here, okay? But epsilon 2, you can see it over here is 0. Epsilon 2 is going to be 0, 2. And the shear strains are going to be 0 as well. But this value is not going to be 0. Okay? I want you to tell me what that value is going to be. But the stress tensor now is going to be, look, there is a stress here. So this one is not going to be 0. And although you can't see over here, but there are stresses preventing that expansion to the sides. Otherwise, it would expand, as we have seen in the unconfined compression test. If you push in one direction, it expands in the other 2. But in this case, it cannot expand in those other two directions. So those two stresses are going to be non-zero values. And the shear strains are zero as well. So the point here is that even though you have shear strains which are zero in these locations, epsilon 2, epsilon 3, stress are non-zero. Okay? The second part of the compressibility, it's also in the notes. You can see an example there about how to solve that problem. It's not too difficult. Okay? So let's talk about the third problem in this homework, which is problem number 5 in the notes. And in this problem now you have to use the Poisson ratio and the Young modulus in order to calculate tectonic stresses according to these equations. Okay, since I'm here, let me show you something. We derived already these equations in class, right? The horizontal stress is going to be proportional to the effective vertical stress through the Poisson ratio. And in addition to that, remember that there's going to be an additional stress value whenever you have tectonic strains. What those tectonic strains mean? They mean that the tectonic plates are pushing in horizontal direction, so those stresses are going to be larger. How much larger? It depends on the value of the tectonic strains, and it depends also on the stiffness of the rock. So I put together these equations here into an animation that, let's see if we can get it to run. It's a Python script. I think many of you are familiar with these Jupyter notebooks, especially if you have taken Reservoir 2 with Professor Foster. Basically here I created a widget that allows you to calculate stresses and to show what is the effect of the tectonic strains. So let me run this. This is available in the GitHub repository. And basically what we have here, let me zoom in, it's a plot of stress, total stress, as a function of depth. So here vertical stress, this is pore pressure as a function of depth and as a function of the Poisson ratio and tectonic strains and a parameter for the pore pressure. So this example, probably I should have started with a more realistic value of Poisson ratio, but now the Poisson ratio is 0. And let me put something a little bit more realistic, like let's say 0.25. And now you can see the values of the total horizontal stresses. Increasing the value of the Poisson ratio is going to increase the value of the horizontal stresses. That means that the rock likes to expand more to the sides, and because of that, the horizontal stresses are going to be higher. Doing hydraulic fracturing in these rocks with a higher Poisson ratio is going to take more pressure than with a low Poisson ratio. So in this example, the tectonic strains are 0, both of them. Because both of them are 0, the two horizontal stresses are the same. Let's add a tectonic strain in direction 1. I add tectonic strain in direction 1, and now look, S11, the green one, well actually you can see colors over there, but this is S11, where I'm moving the mouse. It's going to be larger than S22. And S22 is not going to be the same as it was before without tectonic strains, because although you may push in direction 1, because the rock also would like to expand in this direction, you're going to have an additional stress in direction 2 as well. So it's not going to be the same as without 0 tectonic strains. Let's say that after some geological time, the plate tectonics move again, and now stress coming in the other direction, epsilon 2. So your stress in direction 2 is going to increase. If your tectonic strain is larger in that direction, now S22 is larger than S11. And look, if your tectonic strain is large enough, it could be even larger than the vertical stress. That's when we switch into this other type of stress regimes, in which vertical stress, which is this continuous line, is not the largest stress anymore. But it may be intermediate, or even if now we have more tectonic strain, it could be the minimum principal stress. Now the two horizontal stresses are larger than the vertical stress. And as we were discussing before, you knew the equation whenever these tectonic strains are 0. That's a good assumption in many places. But in many other places, it's not a good assumption. And it doesn't work like that. And you're going to get very bad results if you assume that. In some places, we have something closer to this state of stress than the one with 0 tectonic strain. Eaton's equation, Poisson ratio divided 1 minus Poisson ratio, that is assumes 0 tectonic strains and assumes this case. And in that case, your horizontal stresses are the same, which is also is not what happens in the field, and they have a value which is proportional to that Poisson ratio, that 1 minus Poisson ratio with effective stress. Let me add one more thing. Let's say that we have some tectonic strain like that one, and now I'm going to change the pore pressure. We have seen before that pore pressure is not always hydrostatic. Sometimes it increases with depth because of several reasons. Remember that all these elastic equations, and also what we're going to see later on, equations that assume a failure of the earth crust, they are based on effective stresses. So this value from here to here, or from here to there, is a proportion of that, of the effective vertical stress. If I reduce this value, these ones are going to be smaller in effective stress too, but look, I'm going to increase here the pore pressure, assume that increases with depth. Now you can see how closer they get to the value of the vertical stress. In absolute value, in total stress, they get larger, but in terms of effective stress, they get smaller. And we're going to see later on that a smaller effective stress means a weaker rock. And sometimes that's a problem for drilling, but on the other hand, it's good for reservoir engineering, because lower effective stress usually means higher permeability. Higher permeability means higher initial production rates. Okay, so you can play with this at home today, evening, before you go to wherever you have to go. And it's problem number 5 is just an application of this. Okay, you had a question?
What you mentioned in the video, why was the horizontal stress?
This one? It was changing because this value is always in proportion of this one. Alright guys, have a great weekend. I'll see you Monday.